In the name of God. My name is Mariam Jamshid Nejad, who want to present you a paper by this subject, Influence of Suspended Sediment Concentration and Particle Sizes on the Sound Attenuation of the Fluvial Acoustic Tomography Technique. Abstract Study Purpose Fluvial Acoustic Tomography System, which called FATS, is an advanced technology acquires continuous stream flow data in rivers, even during floods. This study proposed estimation the maximum applicable measurement distance, which called MAMD. This study explored the influence of suspended sediment characteristics and maximum applicable measurement distance of 30 kHz FATS in different rivers with the high variability of SSC. SSC is suspended sediment concentration. This estimation is based on two parts. One, SSC, and second is particle sizes. The study results that MAMD might be 2,380 meters, but in clear water. And the stream flow monitoring can be perfectly done if the SSC be less than 12.67 kg per cubic meter and the particle radius or be 3 micrometer of 3 micrometer and the horizontal distance between two acoustic stations be 100 meter and also the acoustic signal are not perfectly done if the particle radius equal to 20 millimeter and the maximum SSC be 6.6 kilogram per cubic meter. Introduction. Continuous stream flow monitoring is an important hydrological subject in water resource management and environmental studies. Acoustic tomography technique is based on travel time approach and it has introduced for the ocean monitoring since 1979. And after 23 years of AT observation and experience on oceans and the seas, they found that for oceans, the AT system of less than 1 kilohertz and for the seas less than 10 kilohertz. Utilities utilize the ATS in a shallow river for the first time began from 2010. They successfully monitored the stream flow for 44 days by a pair of 30 kilohertz fluvial ATS. And the transmission line was 220 meters. The research background FATS for long-term velocity variation measurement where the acoustic transmission line was 163 meters and in another measured the variability of salt flux where the horizontal distance between acoustic stations were 198 meters. In other, measuring the energy flux in a strait where the acoustic transmission line was around 1,204 meters. And also the others measured the stream flow of a shallow monitoring river using a FATS by the transmission line was about 300 meters. Investigated the characteristics of tidal, tidal discharge and the three tidal channel junctions that needs to use three pairs of FATS, where the transmission lines were 224, 246, and 290 meter. These three different transmission lines. What is ADCP? It's Acoustic Doppler Current Profiler. It's based on application of Doppler effect. It's a routine acoustic device for river discharge monitoring. That transmits acoustic signals. Range is in hundreds of kilohertz to few megahertz. FATS is widely used for long-term river monitoring in low and high flow conditions. The main obstacles and measurements. ADCP is the attenuation of acoustic waves. The energy of an acoustic wave is attenuated by three ways. First, increasing the distance from the source. Second, the energy absorption by water molecules. Third, the energy absorption by the suspended particles. The sound attenuation by suspended solids. The attenuation degree of a signal is non-linearly, depends on the acoustic frequency. The higher frequency undergoes the greater attenuation. Apply three types of ADCPs with different frequencies: 300, 608 kHz, and 1.0 MHz. In a river section by 80 meter width, the maximum measurement range of those systems are 300, 90, and 20 meter respectively. Their study shows that during flood events, if the SSC increases, the signal uh, cannot the signal intensities are attenuated such that the measurement gets impossible. FATS can be preferred to ADCPs because the FATS wave of 30 kHz frequency is able to propagate much longer than the lowest frequency ADCPs in the same situation. The studies showed that the ADCP's acoustic backscatter can heavily affected by first the SSC, second the suspended sediment sizes. It's interesting that the impact of sound attenuation by suspended sediment on FATS is not investigated yet. Materials and methods. FATS is equipped with a couple of broadband transducers of 30 kHz central frequency and the source level of 197 decibel. The horizontal and vertical beam patterns of the transducer are omnidirectional and hemispherical, uh, respectively. The FATS system deduces the average velocity from the multi-pass sound propagation, which covers the whole cross-section between two acoustic stations. The contrast to the acoustic velocity meter (AVM), where the acoustic pass is a straight line. The stream flow is preciously measured due to the omnidirectional, hemispherical beam patterns, and multiple ray methods. A pair of FATS's is set diagonally on both sides of the river. The sound transmitting is synchronized, synchron- uh, syn- synchronized with a GPS, Global Positioning System (GPS). GPS receiver modules that connect to satellite and provide a high standard frequency, 10 MHz. Ensure that the acoustic signals are preciously processed. Each FATS simultaneously emit acoustic pulses modulated with maximum length sequence, M sequence series. M sequence is a pseudo-random sequence that increases remarkably the signal-to-noise ratio (SNR) of received signals. This is a process that this picture we see the river and two source transducers that are in the both sides of the river, but they are not at the same level. They are different levels of the river, and the GPS and satellite that achieve the signals and process them, and for the calculating the theta and the velocity and q the flow of the river, we see the next slide. Okay, we want to calculate the cross-sectional velocity along the transmission line. U, the character is U. For this formula, we need L, T1, and T2 that are horizontal distance between the stations, and arrival time at the upper and lower station. Okay. After that, we will calculate the Q, stream flow, that we must have the A parameter and U. U was calculated, and A is applicable cross-sectional area of stream along the sound transmission line. Theta. In the last section, we have theta. Theta is the degree, is the angle between the transmission line and the stream axis. It's here. Between the U and V, we have the angle theta. After that, the first thing that we must know is it's important to have a flawless data. If the data be flawless and it's better, we will have the most correct and more near answers to the nature situation. The receive level is RL. For to have a RL, calculate the RL, we must have SL and PL. They are source level and propagation loss. That for propagation loss, formula number 4 is the way how to calculate. And that for this formula we will need the spreading loss, and also the loss due to absorption of water molecule and suspended solids, that is with alpha R character, and also L0, and that is the it's all other losses. It's, beside all other the losses, and after this we will have a short formula. It's number 5 that is short. At the next, we will have that the formula number 5, but with two extra things, Na and Gp, that that is showed in number 6 formula. And here, Na is total level of noise which includes the ambient and system noises, and also GP, that is processing gain due to the use M sequence. For having calculated GP comes from a table 1, that's showed in the up of this slide. We look at the table 1. It had it has three sorry it has three columns. First column is M sequence degree, second column is M sequence length, and third column is processing gain. We have the M sequence degree and length, and after that we will have if we have one of these two columns number, we will have the GP that is related, the GP is related with these two thing. Okay, and right, like this, and like this we calculate the SNR. After that we have a coefficient with the name of alpha. Alpha coefficient is which is the summation of sound attenuation. It's include of two parts. The first part is alpha W and the second part is alpha S. That alpha W is water absorption and alpha S is suspended sediment absorption. These two parts plus each other makes the alpha. Alpha is total of these. And okay, and in formula number 8, we saw how to calculate alpha W. It's depend on F. F is frequency of sound. And our study is about this is 30 kilohertz. Okay, and the other parameter alpha S calculate like this, and it depends on the distance and the suspended sediment concentration, and also one other parameter that is the sediment attenuation constant. It's made up of two terms, uh, S and V, and calculated like this showed in formula number 11 and number 12, and they are depends on acoustic wave number calculated, and equivalent sphere radius of suspended particle and density of suspended particles, and we will have these, and after that we solve number 11 and 12 and 10. We can solve the formula number 9. And here we have the other parameters that are dependence on water density, mu, and beta. Beta is a function of angular frequency. Okay, and it's the depend on water dynamic viscosity. After that, after all these calculating these parameters, we want the proposers to measure the attenuation constants. Uh, we compute equation 10 to 16 in the last slides to reach this chart. This chart is about sound attenuation constants as a function of particle sizes. We want to know what's the relation between a grain size and the attenuation constant. The horizontal axis is grain radius, the particle size in the unit of micrometer, and the vertical axis is about it shows in the unit of decibel, the attenuation constant. When we see this chart, we saw the three curves, three different curves. One continuous black, and one dashed black one, and one the other blue. It's the blue line. Okay, what's the difference between these lines? The dashed black line, when we saw, have quantity after 1000 micrometer, but uh, it have not any quantity before a lower for a lower than 1000 micrometer grain size. But it's opposite in black continuous line. At this, we have quantity for lower than 1000 grain size, and for upper than 1000 grain size, we don't have any quantity, and quantity is 0. Okay, and the blue line consists of two uh, other lines, but that part of them that have quantity. We can say that blue line it's a total sediment attenuation constant. Okay. Um, the grain size lower than 1000 micrometer is very small and tiny um, sediments, and the upper than 1000 micrometer consist of bigger sizes for um, sediments. We have two peaks in this chart. The first peak have for small sediments, and the second peak is for bigger sediments. And as you see, the second peak is upper and have bigger quantity. As you see, the uh, first peak is about 1 and 3 micrometer, and second peak is 2 and 20 micrometer, and the she decibel for the first peak is 0.038, and for the second peak it's 0.069 decibel meter per kilogram. Okay, we know something. According to this diagram, the velocity greater than 2 meter per second is able to transfer the 40 millimeter particle. So by knowing this, we can say that during the flood events, if the velocity river be 2 meter per second, the suspended sediment with radius of 20 millimeter, uh, we can measure this sediment in this flowed river, and it's possible, maybe possible. Okay, we have the other chart here. In this chart, the horizontal axis is same as the last one, and the vertical axis is alpha S. Okay, we have the colorful curves inside the chart. Okay, specific tree. It's the relationship of a grain size at a different, and in the vertical axis we have alpha S, and if we have a water sediment free, had no sediment, the alpha S will be 0. It's very clear. As you see, the second peak, the scattering loss zone, second peak, is more amplified than the viscose absorption zone, the first peak. And as you see, also the colorful curves at the first peak have less quantity uh, than their second peak quantity. Okay, the value of the yellow and green ones, as you see, they are very similar, very near to each other, but at second peak they are a little have difference. And a yellow one is 0.1 and green one is 0.2. Here we have others also. If you see blue one, the second peak gets much higher, and it's a higher number, and it's 0.5. And also like this for the uh, last curve, the brown one, we see that the second peak is 5.28, and it's much higher, and alpha S is for this peak, second peak is 0.367, and for the first peak of the brown curve, the alpha S is 0.192. As you see, it's like the second one, it's about 2 times bigger than the first peak quantity for alpha S. Table 2 presents the peak value of difference and the difference between two peak value for each alpha S. Okay, as you see, we have 4 different columns. The first column is concentration, and the 4 columns is the difference between peak 1 and peak 2. And peak 1 and peak 2 are the peak numbers from the last chart, as you see. Peak 1 is for the first peak, and the second one, peak 2, is for the second peak that we talking about. The peak 1 was the grain size lower than 1000 micrometer, and peak 2 higher than 1000 micrometer. Okay, anyway, for instance, as you see, uh, when a first column concentration increasing from 0.2 to 2 kilogram per cubic meter, the last column, alpha S, also rises by 1 order of magnitude from 0.005 to 0.05 decibel per meter. As you see, the rises rate is same, or so near. Determination of maximum applicable measurement distance, MAMD. This was one of my purpose of this study. It shows in the calculation slides in the past, we calculated the SNR. SNR is important um, part of calculating the MAMD. As you see in the table 1 and SNR formula, we measure the other parameter in their different formula for calculating the MAMD by the situation of this study. However, SL of FATS is 197 decibel and alpha W is 0.008. And also, as you see, L0 is assumed to be 10 decibel. GP from this table 1 calculated at 36.1 that it showed that the M sequence length and M sequence degree is 12 and 40, 95 as you see in the table. And anyway, by these parameters, we calculated the SNR and other things. One of the important things that we must notice is about the noises, the other noises in the area. Because the other noises disturb our signals and we cannot um, achieve the signals very good and properly. So we must know the other noises better in the different areas. For example, the ocean, in the shallow water, or in the sea. Other noises, how much than other voices. Although the ambient noise in the ocean and sea is about 55 decibel and 85 decibel, respectively, it can be adversely larger in shallow waters. As you see, at the shallow water, we have a larger noise than in the ocean because ocean area is much bigger and the noise but beside that much big areas get 55, but a shallow water have much little areas and the noises is more than its area. Okay, as you see in some other research that, for example, in the European rivers calculated the noise in the stream at the rivers, and the noise calculated, for example, 45 to 105 decibel plus. For different case studies, it's different, but the range is similar to each other. Okay, we have results. Yes. According to the instrument manual, the operational range of FATS is roughly exceed to about 100 to under 2,000 meter. Okay, it means the minimum length is 100. We don't have less than 100 distance. We couldn't have this, and the maximum length is 2,000 meter. Okay. In 2019, showed the horizontal distance operational range of FATS in the rivers by the widths of rivers is 40, 50 and 70 and 100 respectively. Its horizontal distance is equal 100, 115 and 140 and 180 meter. Similarly, for the river with the width of 200, 300, 400, and 500, the horizontal distance is respectively 320, 460, and 600 and 730 meters. These are the results of the other research. Okay, as you see, when the river wide gets wider, the distance also could get longer. We have longer distance. If the wide is 200, the distance is 320. But when the wide is 500, the distance gets 730. It gets longer. Okay. Fig 4. In Fig 4, we have two different charts. The first chart A, it's for the 3 micrometer size, grain size, and B is for the 20 millimeter grain size. As you see, these two charts are too similar to each other, but have a little difference. The black line is the line that for clear water, sediment free, SSC is equal 0. Okay, and as you see, a red line is so near to the black one. The black line, it's impossible. It's don't happen at the nature. But the red one also it's very ideal. Okay, when you look at the chart in the right hand vertical axis S and R, the range of the S and R is from 10 to 50. The maximum SNR is 50 and the minimum is 10 for both charts. And also um, the maximum SSC for chart A is 12.67 and the minimum is 0. And for chart B, the maximum is 6.6 and the minimum is 0. And from left to right, the SSC decrease and yes, the SSC decrease. And your distance range, the horizontal axis shows us that the minimum distance is 100 and maximum is about 2400. So physically we couldn't have range lower than 100 meter. Okay. And red line is so near to black line, and its concentration, it's show the hypothetical suspended solids concentration of 0.01 kilogram per cubic meter. Okay, and also if you look at the green or yes, green one, the green line. Look at the green line. In A, the green line begin from 200 to 1,500 about near this. And for chart B, the green line began from 200 till 100, 1,000, hundred, one, 1,150 about this or 80. So, as you see, their duration is different to each other, but the SSC is equal for both is 0.2. But the difference of these two is about in the particle sizes. So you see that if the particle sizes is 20 millimeter in green line, the minimum the maximum range of the distance is for the A chart, for chart A is 1,500, and for a chart B is 1,200, and 300 meter difference between them. It's amazing. If the particle sizes be bigger, the distance will be shorter. So if the size be bigger, the distance be shorter. Yes, this we note from this two chart that we see. Okay, MAMDS. And the last thing about MAMD's formula, how we calculate it. All the parameters that we calculate in the last slide, we put all of them in this formula number 19, and then we will have MAMD. Okay, just I must say this. Oh, okay, and I said you that the maximum distance, the minimum distance MAMDs is 100 meter, and the maximum is about 2,000 meter. Okay, I said you the right maximum distance is 2,380 meter for both of them. S1 and S2 is 2,380 meter. Just the chart, the first chart and second chart just have a difference between the grain size and the maximum SSC. Okay, go ahead. Fig 5, the chart with the horizontal axis range distance and vertical axis SSC. Okay, we have three zones. First zone under the red line, below the red line, is the safest, where the acoustic signal would definitely never be lost. Second zone is the area between the red and black lines, is applicable when the particle size is not equal to S2. It's capable for the size for S1. And the zone 3 or third zone is potentially not applicable for using FATS. The third zone is up than black line, above the black line. But one thing that I must add, it's not for even. Therefore, in particle sense, zone 2 or even zone 3 may still be applicable for using FATS as 1 or as 2. Okay? And okay, we have some example of this chart in this page. If you see the chart, the SSC 0.1 kilogram per cubic meter is equal by 1,500 meter. And if the SSC be 0.5 kilogram per cubic meter, the distance will be 1000 meter. And also for um, 2 kilogram per cubic meter, that distance will be 430. Do you see? Okay. And these examples. What is the point A, B, and C? Point A have the SSC equal 0.1 kilogram per cubic meter, and the distance about 1000. The distance about 300 meter. And point B, the SSC is 1 kilogram per cubic meter, but the distance is 360 meter. But the difference between these 3 points is about the kilohertz. The point B have 600 kilohertz, and point C with the SSC 0.1 and the distance with 520 meter, these have the 300 kilohertz. 300 kilohertz frequency. Difference is about for the difference of frequency. As you see in the chart, point 1A and point C have the equal SSC, but different distance. This difference is because of the different frequencies. And as you see in these different points, for point B, we can, because it is calculated from the river that and the floody situation, we can know that if the river be flowed, have a situation, and we can receive the signals if the stations be with this distance 540 meter. And for point for point C, the distance for floaty time can be 800 with this situation, and it's possible to calculate and measuring. The end conclusions. Understanding the impacts of the suspended sediment on the sound attenuation for doing a perfect environmental monitoring during the various conditions. It was our purpose. This study presented that with the 30 kilohertz phases, the suspended sediment can be measured. And MAMD of this system is estimated about 2,380 meter in clear water, that SSC is 0. And the maximum FATS measurement distance is 1,204 meter that has been conducted, and the minimum is 100 meter. Then the potential effect of the cross-sectional SSC receiving the acoustic signals SNR is 10 decibel. And for calculating this MAMDs, we assumed the homogeneous particle size. It's not happen in the nature, but it's ideal. But we were pushed. We must do it because It hasn't happened in during flows, but we need to do this to help measuring. And the suspended particle with different sizes that are located in different zones definitely have different behaviors on the acoustic attenuation. The maximum attenuation for the 330 kHz acoustic waves occur with the particle radii 3 micrometer and 20 millimeter. Okay. In the first case, when a distance between the acoustic stations is 100 meter, the river camp has SSC 12.67 kilogram per cubic meter. This is the maximum without disturbing the FATS performance. Yes, and for the second case, the SSC equals 6.6 kilogram per cubic meter without losing acoustic signal. Abbreviated words and reference was the paper, but the first author, Masoud Bahrini Motlaq, date 2020, and in Journal of Water and Environmental Technology. Thank you so much. Have a good time.